In this video, I'll explain what a null hypothesis is and how it's used in making statistical inferences. Let's first think about the example of flipping a coin. Let's say you flip a coin 20 times and 12 of the flips land on heads. So the parameter is the percent of all flips that land on heads. Now, there are several research questions we could ask. One is, what percent of all flips land on heads? And to investigate this research question, we would make and test multiple hypotheses about the parameter. For example, we might test the hypothesis that 50% of all flips are heads, or 25% are heads, or 40%, or any other percentage. But there is a second research question we might ask, which is the coin unfair? This research question corresponds to the first of these hypotheses about the parameter, because if 50% of all flips are heads, then the coin is not biased. And this type of hypothesis is called a null hypothesis. Let's use this null hypothesis to answer the research question. So we'd set up a model with two elements, heads and tails, and set each trial to simulate 20 flips. Then we'd simulate many repetitions of the trial. Here we'll do 1,000 repetitions. And then we can look at the resulting distribution of sample percentages. So here is our sampling distribution. Our observed statistic was 12 out of 20, or 60% heads. So the p-value would be 50.3%. This is not strong evidence against our hypothesis, so we can't reject the hypothesis that there is a 50% chance of getting heads. So we can conclude that the coin is probably not unfair. Now, it's tempting to conclude that the coin is fair, but then would be saying that exactly 50% of all flips are heads. But there are other parameter values, like 49% and 51%, that would also give us large p-values. Since we wouldn't reject those hypotheses, then we're not concluding that the coin is perfectly fair. We're just concluding that it's probably not unfair. Let's take a look at a couple of other examples. The world-renowned illusionist, Paul the Canadian, claims to have ESP. So you pick a card from the deck without showing it to him, and he guesses the suit. Then you put it back, and you do it again, and again, and again, for a total of 15 cards. He gets the suit correct for 10 out of the 15 cards. So we want to know, does Paul have ESP? In this situation, the parameter is the percent of cards where Paul's guess is correct. So the null hypothesis would reflect the idea that Paul doesn't have ESP, or in other words, that Paul is just guessing the suit of the card. And this is saying that the parameter is equal to 25%, because if he's just guessing, Paul only has a 1 in 4 chance of getting the suit correct. Let's look at a model for this hypothesis. For our model, we'd have 1 correct and 3 incorrect, and select 15 cards in each trial. Then we'd simulate a trial of 15 cards, and repeat that many times. And here is the resulting sampling distribution. Our observed statistic was 10 out of 15, so the p-value would be 0.08%. This is very strong evidence against our null hypothesis. So we would reject our hypothesis and conclude that Paul has ESP, or maybe just a marked deck of cards. Let's look at a few more examples and just identify the null hypothesis without doing the full analysis. You might have heard that in an election, people are more likely to vote for the taller candidates. So you might ask the research question, are taller candidates more likely to win elections? Now, before jumping in, it's going to be important to clarify exactly what it is you're trying to measure to answer this research question. For this scenario, the parameter, which will denote pi, is the percent of all elections won by the taller candidate. So the null hypothesis should reflect the idea that the taller candidate doesn't have an advantage. In this case, if there are just 2 candidates, then the taller candidate should only win half of the elections. And we could model this null hypothesis with a list where there is an equal chance of the taller candidate winning or losing. Let's look at an example involving 2 populations. As music has gotten more portable, people are spending more time listening on headphones. researchers have wondered whether this increased use might be leading to hearing loss. In 1995, they surveyed 2,928 teens and found that 14.9% of the teens had some degree of hearing loss. In 2015, they surveyed 1,771 teens and found that 19.5% had some degree of hearing loss. So we want to know whether there is a difference in the rate of hearing loss. Unlike previous examples, there are two populations, all teens in 2015 and all teens in 1995. So there are two parameters, the percent of all teens in 2015 who have hearing loss and the percent of all teens in 1995 who have hearing loss. And we combine these into a compound parameter by subtracting, and we usually represent this using symbols. In this case, the null hypothesis is that there is no difference between these percentages, that the difference in percentages is 0. And we would create a model for this null hypothesis by combining the data from the two samples. Let's look at one more example. A few years ago, researchers wondered whether swimming with dolphins could be used as therapy for depression. Researchers recruited 30 adult participants with a clinical diagnosis of mild to moderate depression. These 30 participants went to an island off the coast of Honduras and engaged in one of two activities, either swimming or swimming with dolphins. The participants were randomly assigned to one of the two groups. After the treatment, 3 of the participants in the swimming-only group showed signs of improvement, and 10 of the participants in the dolphin group showed signs of improvement. So our research question is, does swimming with dolphins affect depression? There are two parameters, the percent of the participants who improve in the no dolphin group and the percent of the participants who improve in the dolphin group. As before, we'd combine these into a compound statistic, which we can represent using symbols. In this scenario, the null hypothesis is that the treatment has no effect. That is, these participants would improve whether or not they swam with dolphins. Another way to write this is that the difference in percentages is equal to 0, saying that the treatment has no effect. As in the previous example, you would model this by combining the sample data from the two groups of participants. Now, let's summarize what we've seen here. We've looked at several examples of null hypotheses. A null hypothesis is a hypothesis about the value of the parameter that reflects the idea that there is no preference or no effect or no difference or that there is random selection or guessing, although the specifics will be different for every scenario. After specifying a null hypothesis, we create a null model based on the hypothesis, and we use this model to create a sampling distribution. Then, using the sampling distribution, if the observed statistic is strong evidence against the null hypothesis, then we can reject that null hypothesis. So in this way, creating and testing null hypotheses are one important tool in making statistical inferences.